Welcome to Con 305. Our session is about running machine learning workflows at enterprise scale using Kubeflow. Let me go ahead and introduce myself. My name is Peter Dalbunjan, and I'm a container specialist solutions architect at Amazon.
Hi, I'm Mohan Mupidi. I'm Cloud Architect at ML Group at iRobot. If you haven't heard about iRobot, we are the makers of Roomba. We've been innovating in robotic space for around 30 years now. You might have heard some of our products: Roomba, Brava, Luz, Mira, and you might have been using one too. Our robots are smart, cloud connected. They use vSLAM to create a map and intelligently clean your homes. As you may imagine, ML combined with robots can allow us to make some magical features happen. Today, I'll be talking about one such feature and what goes in the background around infrastructure that supports such kind of features.
So here's the agenda for today. We'll start with a typical customer journey in order to run machine learning in the cloud, and we'll touch on iRobot specifics as we go through that journey. Then we will cover evaluation criteria that iRobot had in the decisions that they made in order to choose to run Kubeflow on top of EKS. And we'll touch on one of the use case, recently announced feature from iRobot, which is called as iRobot Genius. And we'll see the type of infrastructure that supports building that machine learning application. Lastly, we will cover best practices and gotchas. Let's get started. So typically, customers start with Amazon EC2. The reason could be because it's the easiest way to get infrastructure from the cloud. You can run certain tooling on your laptop, like an IDE or a Jupyter notebook. You can also spin that up on EC2. Spin up a desired EC2 instance for your machine learning step, whether it's for training a model or for creating an inference endpoint. And then once you're done, you can tear that down. Now, this approach works great for simple use cases. And it's also fairly easy to get started. You can even use tools such as CloudFormation, CDK, or Terraform in order to spin up the infrastructure and quickly tear it down. Now, as you can imagine, it can be difficult as you start running at scale. You also need special expertise at the hardware level in order to get the right performance from your infrastructure. Mohan, can you cover your team's experience working at the hardware level?
Sure, Peter. We did not start with EC2, but we started with something similar. We started with GPU desktop boxes. Our ML engineers were able to run their models, they were able to train, they were able to get some results. Now, as we started scaling up our team, it became a little bit harder to create a consistent environment as the previous desktop box for the next developer. So in a way, scaling up has become harder, and as you know, consistency is really important for experiments, and experimentation. At the same time, we also had issues around scaling up the experimentation itself. There are situations where you might want to run a hyperparameter tuning job, or you want to run experiments at a different scale, like you want to run maybe 15, 20 experiments at the same time, so that you can gather the results and based on that make informed decisions around what you want to do next. And this was hard as well because you only have 2 or 3 machines and you cannot scale up. That's when we started. We wanted to look at different tools that are available and see what works for us.
Now, a quick tip here is if you're going down this path, make sure to check out Deep Learning AMI. What we do here is we package most popular frameworks such as TensorFlow, XGBoost, PyTorch, MXNet, and we offer that as an AMI so that you can quickly get started with building your machine learning application. Now, the second approach is to go with containers. Now, there are tons of benefits using containers and running your machine learning workload, which I'll cover in the next slide. Within Amazon, we have 2 orchestration engines in order to run containers at scale. One is Amazon ECS, or Elastic Container Service, and the other is Amazon EKS, or Elastic Kubernetes Service. Now, both services integrate deeply into AWS ecosystem. Amazon ECS was built by Amazon, and it provides an opinionated API for running containers at scale, and it offers a simplistic way of integrating into AWS ecosystem. Amazon EKS, on the other hand, runs Kubernetes, which is upstream, and it is based on open source distribution. And it brings the most flexible way of running containers using Kubernetes. Now, containers enables you to run your application in a standardized way. It also enables portability. If it runs on your laptop, you can run in the cloud. And it's great to run your machine learning workload alongside your microservices. As you can imagine, you still need to build certain abstractions. The main reason being data scientists may not prefer to learn containers or learn Kubernetes because they want to focus on building their machine learning workload using Python-based toolings and make their algorithms run efficiently on top of cloud infrastructure. Mohan, can you cover your experience working with containers and also touch on AWS Batch?
Our team started out with building a tool around AWS Batch. If you haven't heard about AWS Batch is a batch compute service that AWS provides. It's run on top of ECS. When we started using this AWS Batch environment, we quickly noticed the advantages of using containers in our experimentation. We can preserve the environment, which is great for experimentation. We can scale it up however we need it, given how many resources, like AWS has, kind of infinite resources, which you can just use and scale up. At the same time, we got the benefit of using Spot instances wherever we want to use, and that actually helped us a lot to scale up our experimentation, scale up our development work.
Now, another quick tip here is to take a look at deep learning containers if you're using either of those orchestration engines. Because what we do here is we package popular frameworks, like I said, TensorFlow, MXNet, and XGBoost, and we offer it as a container so you can readily get started with Amazon ECS or Amazon EKS. Now, the third option is to use Amazon SageMaker and purpose-built machine learning service that is offered as an API. Now, what do I mean by purpose-built machine learning service offered as an API? Let's say, for example, you're building an entertainment application that captures videos or pictures of celebrities. You can use Amazon Recognition in order to identify those celebrities from your pictures or video streams. Now, Amazon SageMaker is a great service. It offers you all the tools that are required in order to run your machine learning workload in AWS, and it gives you fully managed infrastructure. And it offers built-in support for algorithms and frameworks such as TensorFlow, MXNet, or PyTorch, and it offers managed Spot training. So let's say if you want to run a training job using the least compute infrastructure using Spot instances, SageMaker gives you an API in order to do exactly that. Now, customers have told us that even if you use SageMaker, it's hard to maintain consistency across multiple environments. And you need additional set of toolset if you want to run SageMaker both in on-premises and in the cloud. And also you need additional tooling for workflow management. Let's say your machine learning workload has multiple steps. You need some kind of a workflow in order to manage each of those steps. Mohan, can you cover your experience working with SageMaker?
When SageMaker was announced by AWS, uh, it had almost all the features that our AWS batch tool that we built provided. One of the things that we were really missing was workflow orchestration. So for that reason, we started looking into services within Amazon that will allow us to orchestrate our workflows using either batch or AWS SageMaker. We ran some quick experiments and some prototype work on step functions, and we decided that it's a little out of our ML engineer tool chain. That's when we started looking elsewhere, and we wanted to find a tool that works for us. When we started looking at these tools, we had certain evaluation criteria in our mind, and let's go over the evaluation criteria now. First of all, iRobot is committed to serverless. Wherever we can, we use serverless architectures. It allows us to like build quickly, make the infrastructure manageable as much as possible. If you heard one of the talks from our senior cloud robotics scientist Ben Kehoe, you know we are pretty much into serverless architectures. So as a priority, we had that in our mind. We wanted to see if this service that we're going to use for our machine learning infrastructure is going to be serverless. Along with that, we had several other things in our mind as well. One of them is we need workflow orchestration for sure. We wanted to abstract away infrastructure from our ML engineers as much as possible. We want them to work on their neural network architectures rather than thinking about cloud architecture. We want them to stay within their comfort zone, in the sense that we want them to read papers and implement new architectures rather than thinking about, oh, now I need to learn cloud formation or IAM. We want them to just use Python and C++ that they're familiar with and build something that works for them. We want this infrastructure to also be deeply integrated with AWS, because most of our infrastructure is on AWS. It makes sense to have your compute wherever your data is. During this journey, that's when we came in contact with Kubeflow. Kubeflow is a open source machine learning ecosystem that allows you to train your models, do data processing, even serve your models as well. Kubeflow runs on top of Kubernetes. Of course, it's not a serverless solution, but given that we can run it on EKS, which is a managed service, it makes it a little bit easy. So given Kubeflow was giving us much more, most of the items that we desired, we thought, okay, we're going to put aside serverless for now and just like run it on top of EKS and keep going with it. So the solution that we came up with is running Kubeflow on EKS. Amazon has been working tirelessly to make it easy to run Kubeflow on EKS. They've added several things over the course of over the time period. Peter, can you share some of the integrations that AWS added to EKS to make Kubeflow integration easy?
Absolutely. Now, before I start talking about how we integrate Kubeflow with AWS ecosystem, I want to highlight that we are committed and we actively contribute to Kubeflow project. The reason for us is simple. We want to give the best experience for our customers to run Kubeflow on top of AWS. Now, because EKS integrates deeply with AWS ecosystem, it makes it easy for us to build integration between Kubeflow and EKS and inherit the features from all the Kubernetes into Kubeflow. For example, if you want to use storage services such as EFS or FSX, you can use the CSI driver project, which we've written for the Kubernetes community, and EKS inherits that. You can use the storage services readily with Kubeflow. We've also built purpose-built integration with certain use cases, such as Amazon Cognito and SageMaker RDS, which I'll cover in the next slides. Now, the first thing the customers are going to ask, if I want to run Kubeflow on top of AWS, how do I make sure that it is secure and give access to data scientists and take the undifferentiated heavy lifting from them? So in order to do that, we added the capability so that Kubeflow integrates with Amazon Cognito for authentication purpose. And because Cognito, you can go ahead and store your user identities locally on Cognito, or you can federate your corporate identity into Cognito. You can build that secure way of accessing your Kubeflow dashboard. If you don't want to use Cognito, you can use the open source authentication mechanism that is built using DEX, which is the default option right now. And you can access your Kubeflow using that security. Now, if you want to offload your certificate management, such as TLS for HTTPS traffic for your Kubeflow dashboard, you can use ACM for that purpose. Now, the second thing that customers ask us is, once I have access to Kubeflow, if I want to access other AWS services, how do I make sure I granularly control access to services such as S3 or SageMaker? In order to do that, we announced a capability for Kubernetes community called as IAM role for service account. You can enable IAM role for service account using the bottom left-hand corner of the code snippet there, and which comes by default if you follow the Kubeflow documentation. And you can fine-grain access control, carve out an IAM policy, and have appropriate permissions delivered in order to access other AWS services. Now, the other thing that customers ask us is, how do I access the storage offerings from Kubeflow for things like data processing needs or even for notebook sharing needs? So if you want to do for those two use cases, you can use Amazon EFS, which is a shared file system built based on NFS, and you can use that with Kubeflow. Now, if you want to keep all your data on S3 and have a high I/O caching layer built between your data processing needs and your compute layer, you can take a look at Amazon FSx for that purpose. Now, the other unique capability that we've built is for Kubeflow customers is, if you look at Kubeflow installation, it installs a bunch of stateful pods. You'll see a bunch of MySQL pods that are running in your Kubeflow installation. If you want to offload those MySQL pods and you make use of a highly available database engine such as Amazon RDS or MySQL or Aurora, you can take a look at the documentation. That way you can reliably store your metadata from your pipelines or Katib experiments, jobs, all of that state can be stored in Amazon RDS. Similarly, if you want to store your pipeline artifacts, such as packages that you access, metrics, and views on top of Amazon S3, that integration is also built into Kubeflow. Now, how do I access Amazon SageMaker for certain things that is really well known for doing things like training or even capabilities such as managed spot training? There's a couple of ways to do that. Now, let's say you're a Kubernetes customer or an EKS customer, and you want to offload some of the training jobs or even run your inference endpoints on top of Amazon SageMaker. You can take a look at Amazon SageMaker operators for Kubernetes. Now, if you're a Kubeflow customer, and if you want to run certain steps within your workflow, within your Kubeflow pipeline, let's say if you want to run training jobs on SageMaker while you run inference on Kubernetes, you can make, that's possible using SageMaker components for Kubeflow pipelines. Now, let me just summarize what we've covered so far. We went through a typical customer's journey, and we touched on iRobot specifics as we went through that journey. We touched on iRobot's evaluation criteria that they had and why they choose Kubeflow on top of EKS. Now, Mohan, can you cover the iRobot Genius machine learning features that was recently released and talk about the architecture that supports that infrastructure?
Sure, Peter. Before talking about iRobot Genius, let's talk about a feature that we've released a while back. If you are one of our customers, you might have heard a feature called as clean zones, where you can, from the app, draw a rectangle on your map and say, this is the region I want you to clean, and robot will go and clean in that area. So with iRobot Genius, we've released a set of intelligent features, and there was a massive app redesign as well, giving more importance to personalization and control. Among these features is a feature called as precision clean zones. Now our robots can use machine learning to intelligently place some of the frequently soiled areas in your map, in your home on the map, and give you a suggestion to set it as a clean zone. If you set it up, then your robot, you can just go to one of the voice assistants like Amazon, Alexa, or Google Home, and you can just say, "Hey Alexa, ask Roomba to clean under the dining table," or ask Roomba to clean in front of the couch, and Roomba will take care of the messes for you. Now that we've talking about depression clean zones and what happens in the future, let's understand how we build this model and what goes into building this model. As with every machine learning team or machine learning engineer, we start with data. We have data infrastructure. In our case, our models take a image and they give out some kind of an inference. So we have images, we have labels for those images. So there's a data pipeline that creates a data set for us. And then there is, in the next step, we take the data, we train it, we get a model. We convert the model to an embedded model that can run on a robot. And then we evaluate the model and make sure the model is on par or better than the previous models that we have developed. Towards the end, we run a system level evaluation with the model and make sure the system doesn't break with the model. When I say system level evaluation, let's talk about the clean zone itself, right? In clean zone, robot is going around, it's looking at different things, and finally in the map, it's saying, this is where the clean zone should be. And it knows like that's in front of the couch or under the dining table. So we want to make sure a robot is placing the clean zone as close as possible to the reality. So we somehow calculate the difference between the reality and whatever has been projected, and that's presented as a KPI to our decision makers, so that they can go and say, okay, this model is good enough, let's get it out, or this model is not on par, let's scrap it and build a better model than this. That's one example of a KPI, right? There are several other KPIs this pipeline outputs, and we use those KPIs to decide whether or not the model should be deployed or not. Another thing to notice in this diagram is, if you can see it, it's a workflow, right? We first build the data set, then we train, and then we run the evaluation. In reality, this workflow is split into three different pipelines. We have a data set pipeline that builds data set. We have a training pipeline that gives us a model along with some evaluation metrics, and then there is a system level evaluation pipeline. The reason why we split it into three parts is because you can create a data set and you can train any number of models in it. That's one split. And you can create a model and you can run any number of evaluations on top of it. That's where the system level pipeline split comes into picture. Now that we spoke about how at a higher level our model development is happening, let's talk about the infrastructure that's actually supporting these pipelines and this workflow orchestration. As with anyone, we started out with basic Kubeflow architecture, where you have a standard VPC with public subnets, you have a cognito for authentication, and then everything kind of works. It's just a basic starter template that Kubeflow provides you. The thing with this is you have to do manual deployment. Testing between dev and prod environments is kind of iffy. Every time you want to update or deploy, you need to go through all these steps. You need to make sure your VPC is right, your EKS cluster is deployed properly, cognito user pool, then deploying the Kubeflow finally after the other steps. In between, if something got messed up, then it's going to take you more than an hour or two to figure it out. So the problem is the configs were all over the place. So we did not have deep visibility into what went into this cluster. Sitting and babysitting in these deployments can be really, really hard. The authentication that we are doing provides different identities than our corporate identities, which can get confusing, and it's not usually a good practice either amongst the other things that I mentioned in this slide. So we took a step back, and with the help of AWS team, we started thinking about how we can make this better. First thing that we did is we wanted to have a continuous delivery pipeline that allows us to deploy Kubeflow on EKS repeatedly. So there'll be a Git repository. Anyone wants to push a feature into this cluster, they have to open a feature branch. There'll be a code review. After the code review is done, the merge happens, and finally the deployment starts. Code pipeline will take care of the deployment for us, and then finally the infrastructure is just deployed. That's one big change that we've done, right? We made sure all the infrastructure we're deploying is getting tracked as code in Git. And the second thing that we changed is the architecture. As you've seen, the previous architecture is not good. If you're a company, you don't want that architecture. So working with our internal security teams and privacy teams, along with AWS team, we came up with this architecture. This is where you have a VPC with only private subnets. You use transit gateway from the VPC to connect to your corporate network so that you can access internal resources. Then your private subnets can actually talk to internet via a third-party firewall, so that you know exactly what's going on there. And then you attach a SAML identity provider to Cognito, which will make sure that you can use corporate identities for logging into Kubeflow and using it. Along with that, we made some other changes around storage. All the stateful apps of Kubeflow, we started using AWS services, using all the good work that AWS team has done around the integration for RDS, EFS, S3, so on. So with the current deployment, we can deploy everything within the infrastructure is tracked as code. We can use a CD deployment to go take care of deploying. It used to take like 1 to 2 hours at times. Sometimes if things go crazy, it used to take 4 hours, but now it's like 15 to 20 minutes, you have the cluster all set, as long as everything went right? We have enough checks in the pipeline so that happens. And then the VPC is more secure, and we can even revert changes if it's necessary. During this journey of starting with something new and then building a CD pipeline, improving the architecture a little bit, we had a lot of learnings, and we wanted to present the learnings as part of this talk as well. So I'll be talking about some best practices and gotchas that we ran into. In our pipeline, we always like to scale our worker node groups to 0. If you're not using the resources, there is no point in actually keeping a node live in a node group. And another thing we've done is we made sure that we separated the control plane node group from worker node groups. The reason being, we wanted control plane to have all of its resources to itself, and not get bombarded with any nodes from worker node. So for this separation, we make sure that we use stains and tolerations, and also labels to make sure we targetedly deploy things. So what we do is we add a taint on worker node groups, so that control plane nodes don't leak into worker nodes. Because of this, if a control plane node pod actually leaks into worker node groups, then there's a chance that the scale up will be interrupted. We don't want that to happen. And we made sure we use labels whenever we deploy labels, and proper toleration on the worker pods whenever we deploy worker pods, so that they'll be targetedly deployed in a specific worker node group rather than a control plane node group. Logging is very important. You can run into a lot of issues if you don't have logging enabled. So we made sure we are using Fluentd to stream our logs into CloudWatch. One of the gotcha here is when you use Fluentd, it can stream everything and anything that's available in the cluster, and that can actually hurt you. In the initial days, it was costing us more than the cluster expense itself, so keep that in your mind when you do this. So add enough filters and stream only what you need. Maybe component logs and maybe autoscaler logs, and some things around kubelet logs, but not everything and anything. That will save you a lot of time. Along with the infrastructure best practices, we have also identified some best practices around usage. So when you're using, if you're coming from outside, if you're coming from outside of AWS, you might know or not know that EBS is a block storage, but you can only have one component container attached to it at a point in time, which means in a pipeline that doesn't have any concurrent components, and if the components are sharing data, you can use EBS volume. It works great and it's amazing. But if you want concurrently running pods to use the same volume, you might run into issues and it's not going to work. For that, you might want to use EFS. EFS is great if you want to access the same data volume for concurrently running pipelines or concurrently running pods. It works great. One of the things with Kubeflow is that you can create some common components and share it amongst your teams. Like we have several teams within ML, and if someone creates a component, and if it can be used by anyone else, so we kind of create a common component and share it amongst ourselves as a Python library. It's actually great. For example, you can create in our case, right? We can create a component where you have this secure area where some personally identifiable information is stored, and you don't want that to be accessed in an insecure way. In that scenario, you can create a component that takes care of all the security checks and make sure you're getting the right data in the right way, and you can share it amongst others who actually need access to that data. And with a simple Python call, they'll have it as part of their pipeline, and everything will be good. There are several use cases for common components. An example of a common component would be SageMaker components, right? So, SageMaker team provides you SageMaker components where you can offload some of your component workload into SageMaker. Uh, it's great whenever you want to offload workloads. Just use it. It just works. One of the hidden features is KFP SDK transformers. This is very useful for, for example, setting up some common configuration for all the component pods in a pipeline. An example for this would be every pod that we deploy as part of a pipeline, we want to make sure it's deployed on the worker node group, which means we need to add a toleration uh, that tolerates the taint on worker node group. For that, like we have a transformer that takes care of it. We don't have to worry about it. You can go a little bit fancy where what we've done is we have a transformer that actually builds the Docker image whenever you start compiling the pipeline. That way, your component images are in sync with your pipeline configurations as well, and it works great. So definitely don't forget the transformers. That is all I wanted to share today. Peter, can you talk more about the resources?
Yeah, absolutely. So thanks, Mohan, for walking us through your Kubeflow architecture and also for covering best practices and gotchas. I think it's going to be helpful for our customers. And if you want to learn more about how to run Kubeflow successfully on AWS, please take a look at the documentation. And also, there is some resources available here on the slide for you. Thanks a lot for attending our session. And please fill out a survey. Let us know how we did in order to improve future sessions. Again, thanks again for attending our session and have a great day. Bye bye.